In this video, we're going to introduce random variables and then specifically talk about discrete random variables. So a random variable is a variable that has a single numerical value determined by chance for each outcome of a procedure. And random variables are usually denoted by capital letters like X or Y. So here are a few examples. If our experiment is to throw 2 dice, then we could let the random variable X be the sum of the 2 dice. So X could be 2, 3, 4, all the way up to 12, or the possible values that X could take on. The value of X is determined by chance. As another example, we could do the same experiment, throwing 2 dice, but we could instead let Y, the random variable, be the largest of 2 dice. And then, Y could be 1, 2, 3, 4, 5, or 6. And again, the random variable Y is determined by chance. As another example, we could flip a coin 3 times, and X, the random variable X, could be the number of heads. X could then be 0, 1, 2, or 3. And as another example, we could survey 500 individuals with a yes-no poll. Z could be the number of yes responses that we get. And last example, if we randomly select a red pine tree from Clarksburg State Park, we could let H be the height of the tree. Because we've randomly selected the tree, that the value of H is determined by chance. A probability distribution gives the probability for each possible value of the random variable. And a probability distribution can be expressed as a graph, as a table, or as a formula. Let's do an example where we express it as a table. So in our example, say we roll a die twice, and we just assume this is a 6-sided die. Let's let X be the number of 5s that we roll. So we can express this as a table, and our table will contain each possible value that X can take on and the probability that X takes on that particular value. So the values that X could take on, we're rolling a die twice. So how many 5s could there be? Well, there could be no 5s. It could be the case that neither of those dice is a 5. There could be 1 5, or there could be 2 5s. So those are the possible values that the random variable X could take on. Now let's find the probability of each of those values. So the probability that X is equal to 0 is equal to the probability that neither of the dice are 5s. So first not 5 and second not 5. So die rolls we know are independent events. So when we think about the probability of one thing occurring and another thing occurring, because these are independent, this is just equal to, by the multiplication rule, the probability that the first is not 5 times the probability the second is not 5. And so what is that? Well, there are 6 sides of the die, so out of 6, and then all of the sides aside from 5 are not 5. So 5 of the 6 sides are not 5s. And for the second die, 5 of the 6 sides are also not 5s. So 5/6 times 5/6, we multiply across the numerators, multiply across the denominators, we get 25 out of 26 is our probability that the random variable X, 25 out of 36, sorry about that, 25 out of 36 is the probability that our random variable X is equal to 0, that neither of the 2 dice showed a 5. Similarly, we can find the probability that X is equal to 2. We can also find the probability that X equals 1, but I'm going to leave that one for a moment. So probability that X is equal to 2 is probability that first is a 5 and the second die is a 5. So again, because these are independent events and by the multiplication rule, this is the probability that the first is 5 times the probability that the second is a 5. And so that is the probability the first is a 5, 1 out of 6, one of the sides is a 5 out of the 6 sides, times 1/6. And so that's multiplying across the numerators and the denominators gives us 1 out of 36. So this is 1 out of 36. And finally, to find the probability that x is equal to 1, so that we can find in two different ways. One way is to notice that the probability that x is equal to 1 plus the probability x equals 0 plus the probability that x equals 2, well, that's the entire set of possibilities for the value of x. So if we add up all the probabilities, we know this must be equal to 1 because one of these things must happen. This is certain to occur, and these are also mutually exclusive events. There can't simultaneously be no 5s and exactly 1 5. So this is certain to occur. These are mutually exclusive events, so the sum of their probabilities is going to be equal to 1. And therefore we could use that to say, well, that means that the probability that x equals 1 plus the probability that x equals 0, that's 25 out of 36, plus the probability x equals 2, that's 1 out of 36, is equal to 1, that's 36 out of 36. And so that means that the probability that x equals 1, we could subtract those values to the other side. So this is 36 over 36 minus 25 plus 1, that's 26 over 36. And so the probability that x is equal to 1 is 10 out of 36. So 10 out of 36 is the probability that there's exactly 1 5 in 2 die throws. Just for practice, let's also calculate that in a different way. So let's also calculate the probability that x equals 1 without using that idea of the complement. So this is equal to the probability that either first is 5, second is not, or the first is not 5, the second is, right? Because if there's exactly 1 5, then either that means the first was a 5 and the second wasn't, or the first is not a 5 but the second was a 5. So that's equal to the probability that the first is a 5 and the second is not. So probability first is 5 and the second is not, so times the probability second not 5, or goes with addition, so plus the probability that the first is not a 5, and so times the probability that the second is a 5. And so that then would be equal to probability that the first die is a 5, 1 out of 6, times probability the second die is not a 5, that's 5 out of 6, plus probability the first is not a 5, any of those other values aside from 5, 5 out of 6, times the probability that the second die is a 5, that's 1 out of 6. And so what do we have all together? We have 1 times 5 is 5 out of 36, plus 5 times 1, 5 out of 36, and that adds up to 10 out of 36, which is exactly what we had above. So this is our probability distribution for x. It gives each of the possible values of the random variable x and the probability that each of those values occurs. There are two different types of random variables, and these are discrete random variables and continuous random variables. So a discrete random variable is one that has a finite or countable number of possible outcomes. So, in our last example, x could be 0, 1, or 2. So it had a finite number of possible outcomes, 0, 1, 2. That's a finite or countable number of outcomes. Even when we say countable, what that means in mathematics is that we can say, okay, there's, the 100th one, and then the 101st one, and then blah, blah, blah. So even if there's an infinite infinite but countably infinite number of possible outcomes, we still consider that discrete. And so by countably infinite, I mean, we can say, a million and one, a million and two, and so on, versus what's the opposite of that? The opposite of that is a continuous scale. So a continuous random variable is one that's on a continuous scale. So a continuous scale would be, say, like weight or height or time. So for any of those types of random variables, we could say, okay, did that tomato weigh like 28 grams, or did it weigh, 28.02 grams, or did it weigh 28.009 grams, or so on? So in other words, there's this continuous scale with no gaps, a continuous scale with no gaps. And so there's infinitely many possible outcomes on a continuous scale with no gaps. That's what we call a continuous random variable. And some things that are always continuous would be, for example, height, weight, time. And again, that compares with, say, a discrete random variable that is finite or countably infinite, where we can say there are gaps between what are the possible values. A million and then a million and one, there's a gap of one between those possible values. So here's a few examples of random variables. I'd like you to take a moment and think about whether they are discrete or continuous, and then I'll go through each one. So first random variable x is the number of heads in 3 tosses. T is the time it takes to finish an exam. X is the number of leaves on a randomly chosen oak tree. Y is the height of a randomly chosen oak tree. C is the cost to produce a bag of potato chips. And Z is the number of eggs a chicken lays in her lifetime. So pause, think about those for a minute, and decide whether they are discrete or continuous random variables. Okay, number of heads in 3 tosses, that is discrete, and it's discrete because there's a finite number of possible outcomes, finite number of possible values that the random variable x could take on. So for x, and those values are 0, 1, 2, and 3 is the number of possible heads we could have in 3 coin tosses. So that is discrete, a finite number of possible outcomes. T is the time it takes to finish an exam. So that is continuous. It is continuous because it's on a scale that has no gaps. So, did it take somebody 50 minutes, or did it take them 50.23 minutes, or whatever? So the precision of how precise it is only hindered by how precise our timekeeping device is. So we think of time as being on a continuous scale. X is the number of leaves on a randomly chosen oak tree. Well, there's no upper bound, there's no limit, but still we are going to think of this as discrete. So if we say number of leaves, we're not talking about half leaves and, 0.26 of a leaf or whatever. We're just saying it's a leaf or it's not a leaf. And so how many leaves could there be? There could be 0, there could be 1, there could be 2, ... There could be 312, there could be 313, etc. And so even though there's no upper bound, this is still discrete because this is not a continuous scale. There are gaps. Y is the height of a randomly chosen oak tree. So we've got our nice tree, and what is its height? Well, its height, again, is on a continuous scale. Was it 20.3 feet or whatever? And so this is continuous. Cost to produce a bag of potato chips. So we do think of this as continuous, and certainly it's arguable, but in general we model cost as a continuous random variable. If you think about producing a bag of potato chips, maybe it costs say $33 to produce 100 bags of potato chips. And so that's costing like 33 cents per bag. Or maybe it costs $33.02. Like if you're being really specific, like there's no like limit to how precise we could end up being. So this we do think of as being on a continuous scale. It's not like that it must cost $0 or $1 or $2 or whatever. It could be any value in between on a continuous scale. And finally, number of eggs a chicken lays in her lifetime. So that could be 0, or it could be 1, or it could be 2, ... And it could also be, maybe this chicken lives a very long time, 1,040 and 1,041 and so on. And again, there's no particular upper limit, but there are gaps between these possible values. So this is not a continuous scale, it is discrete. It is discrete. This is a discrete random variable. In this module, we'll be focusing on discrete random variables, and on the next module, we'll focus on continuous random variables. So for any possible value x of the random variable x, one thing is going to be true about it, that the probability that x is that particular value is bounded above by some number and bounded below by some number. So I'd like you to figure out what those values are. And also the sum of the probabilities, the sum, we could write like that, of all the possible values for x is going to be equal to what? So I'd like you to pause just for a moment and think about those. Okay, so that you may recall that the probability of any event is always going to be less than or equal to 1 and greater than or equal to 0. So an impossible event has probability 0. A event that's certain to occur has probability 1. So that's still true for possible values x of a random variable, capital X. Part 2, the sum of all probabilities is going to be equal to, so the sum of the probabilities of x for each possible value of the random variable x is always going to be equal to 1, because we know that one of these values is going to occur, and these are disjoint values, like either x is equal to this number or that number or that number or that number, and so the sum of all the probabilities will be equal to 1. So based on that, let's take a look at the following tables below, and I'd like you to think which of the following could be probability distributions. So take a look at those, pause, and we'll talk about them in just a moment. Okay, so which of these can be probability distributions? Okay, we've got our probabilities on over here, and yes, this is between 1 and 0, so that's good. This is also between 1 and 0, that's good. This is also between 1 and 0, that's good. If we add up those probabilities together, we've got 0.4 plus 0.3 plus 0.4, and so that's equal to 0.8 plus 0.3, that's 1.1. And we've got an issue here. The probabilities did not add up to 1, so no, this cannot be a probability distribution because the probabilities did not sum to 1. Let's look at this example. So here we've got our probability between 0 and 1, and this is also between 0 and 1. This is also between 0 and 1. Great. If we add those probabilities together, 0.3 plus 0.3 plus 0.4, that gives us 1 when we add this together. Good. These values for x, the values of the random variable, are negative. That is okay. So x could have negative values, like for example, if x is like the amount of money that you win or lose, we would like assign positive values to winning money usually and negative values to losing money. So that's just one example of, the possibility of x being a negative value. And so it's fine for the values of the random variable to be negative. It's just that the probabilities cannot be negative. So this can be a probability distribution. And our last example, we've got our probabilities, and here we've got negative 0.3 is less than 0, and so our answer here is no. We have a negative probability. And the reason that we had no over here was that probabilities didn't add to 1.